Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. Well, I want to bring you this video, bring you updates on the air temperature and sea ice, what the latest data is indicating. I actually wanted to, and I had plans to post this video much sooner. Ran into a major software problem, glitch, whatever you want to call it, where it told me I was recording, and it recorded absolutely nothing after the first 2 minutes. And I did not find this out until I went into the edit mode. And needless to say, I was not impressed. And I had just been having complete shit luck with software lately, and it's ticking me off to say the least. So let's get into this. Nevertheless, this information is still important as it's still indicating what's going on. And then, well, I can even, since with the delay in getting this video out, I can tell you what the hell happened here in Alaska in the month of April. That was entertaining. So let's first of all, let's look at sea surface, not sea surface, surface air temperature anomalies. And this is being related to 1951 to 1980 mean. So the left-hand figure is for December 2020. The middle is from October, November, December 2020, and then a comparison to the year 2020. This number that you see up here is 0.81, 0.94, 1.02. That's the average above this 30-year mean of 51 to 1980. Now, usually what the meteorologists do is they'll do something like, 1951 to 1980, and then they'll do 1961 to 1990, 1971 to 2000, 1981 to 2010, and now the new one that they're calculating out for the 30-year mean is 1991 to 2020. But what's happening is that because the planet is warming, when you compare to those running 30-year averages, we're not really seeing how drastically much warmer the planet has gotten. So I'm now seeing a trend of comparing everything to 51 to 80, and there you can see dramatically how much things have warmed up since then. So looking at the scale here, the scale's the same. If you're in the purple and blue, it's cooler than this relative to this 30-year average. If you start getting into the yellow, tan, brown, brick, red, orange, whatever the color is, dark brown, then you're warmer than relative to this 30-year average. HTTP Columbia.edu. This is the data source for this graphic here. So what do we see here? Look at the Arctic, especially December 2020. It was blazing hot. And when you compare October, November, December, this is the Arctic Ocean up here. This is 6 to 9 degrees C above this 30-year mean. Why is that? Well, there's no sea ice. So the ocean is absorbing the heat, and now the heat's being released. And then when you look at the overall for the annual, we still see that it's about 2 to 4 degrees C warmer than the 30-year average. Now, these values here are for the entire planet. I'm focusing on the Arctic because, as we know, the Arctic is warming. The data now tells us 3 times faster than the rest of the planet. And you can clearly see that. I mean, if you just look at, say, the Americas here, right, 1 to 2 here, and then you get up into the Canadian Shield, the Arctic Ocean, and we're 6 to 9. So that's 3 times faster. Got some cool spots here. This is in the Pacific here. This is reflecting the La Nina conditions that were in place. So that's why we see a little cooler than usual. Same thing here for in December. You notice that for the year, it's kind of about average because it switched from El Nino into the neutral, then to the La Nina phase here. Interesting, cool spot, uh, basically just east of the Caspian Sea. Um, so that's interesting. I'm not sure why that is, but it's there. For the year, though, overall for the year, it seems to have been a bit warmer. So something happened that it cooled down for the last 3 months of 2020. Might have been something to do with the Himalayas, what have you. You'll notice, of course, the perpetual cool spot off Greenland. And that's because you're dumping in all that fresh melt water, which is right at 0 C, and that's going to cool the air above it. So that's almost a perpetual state of affairs these days. So we see you're looking at overall even Antarctica is a little warm. We got a cool spot here. This is, by the way, where you have the Antarctic bottom water that comes off the continent. That's why that's a little cooler there. But yeah, the whole planet is reflecting uh, a warming of 1 degree C above the 51 to 1980 average temperature. When you compare it to the start of the Industrial Revolution, this is even higher. So this is what's going on. Now we're doing the same thing, but now we're looking at January, then we're looking at November, December, January, and then February 2020 through January 2021. So sort of like a moving 3 month and a moving 12-month average. And we again see extremely warm conditions in the Arctic. Very warm conditions in the Arctic. Um, this is very interesting that the East Siberia and Central Siberia kind of cooled down after the historic hot temperatures they experienced in summer 2020. Same data source, Columbia.edu. And again, we see that we can actually see this starting to break down of the La Nina moving into the neutral phase, and we kind of see it's in the neutral phase right about now. Indications currently are that it's moving into an El Nino, but not a very well-defined El Nino. That's present condition. Of course, that could change. Notice, however, the scaling has changed. In the prior panel, it was about 6 to 9, 6.4. Now it's 7 to 10.4, 7 to 9. So it was seeing this is even warmer temperatures here. So again, January 2021, 0.86 C warmer relative to that 30-year. November, December, January, 0.92 C warmer relative to that. And for the 12 months starting from February 2020 to January 2021, 1.02 warmer C warmer than this. So basically, the data continues to affirm that the planet overall is warming. So let's look at record-breaking global temperature over land areas in 2020. And the data is courtesy of the Goddard Institute of Space Studies, NASA.gov, so GISSs. Okay, annual land temperatures. And now this goes back to 1880. It's basically a 140-year record. And as we can see, it's been pretty much increasing. Little bit of a leveling off about in the 1950s or so, mid 60s, and then it starts picking up again. And what you see, this is the dotted line is the smoothing, right? That's the smoothing here. Again, it's compared to 1951 to 1980 baseline. Zachary Labe, our good friend Zachary Labe, created this. And the Goddard Institute Space Studies, GISS. And the orange is basically seasonal variations. You still have summer and winter and so on. So what's the surface temperature anomalies? It goes from 0 is basically this baseline, 51 and 1980. So it goes from half a degree C below, and according to this is about 1.4 at that dot right there above baseline. It's warming, and you'll see how the slope is really has increased. So the rate of change has increased. And you look at now, which is when is this? At the end of through December. So this is like December 31st, going into it's like 1.5. So people saying, "Oh, let's try and keep the Paris Accord, keep it to under 1.5." Ain't happening. So now we're going to look at data sets from scientific centers around the world. All agree that 2011 to 2020 was the warmest decade on record globally. And you can go climate.copernicus.eu. That's where this graphic is courtesy of. And these are the various data sets. And as you can see, they're pretty much in agreement. But here's the point. Here's the baseline. And you can see that 1851 and 1860 is cooler. 1871, that decade's about average. Same here. It's just a little bit cooler. But then when we get into starting in the 1930s, we start seeing it's above the baseline. And then look what starts happening when we get into the 70s, 80s, 90s, and so on. It's just going whammo, increasing quite dramatically. So this is the mean surface temperature change over the industrial area. Now a note here, when they're talking about mean surface temperature, that is taken to be 2 meters above the ground. That's the convention. So they're measuring air temperature at 2 meters above the surface. So if you're on land, above the ground. If you're on the ocean, above the ocean. So that's what that's taken to be. But the trend is unmistakable. The planet's warming. And we can trace it to the start of the Industrial Revolution. So here's another look at it now. 12-month running mean. So they, just like I did at the outset here, we had, January through December, then February through January, then you do March through February, et cetera, and you calculate the average for those 12 months, and that's what's called a running mean. And our planet's rising temperature updated through January 2021, which is right here. And this is anomalies. Okay? And here's that 2 meter level, right? And we're going from 1980. So this graph starts in 1980 and it goes through basically end of 2020. Baseline is 1991 to 2020. So they're actually comparing things to this 30-year average. And what we're seeing is that for the most parts, since about 05 or so, a couple of years, this is like a strong La Nina here, another La Nina, not as strong, but we're seeing how much warmer things are. Now, again, you say, well, it's not even quite half a degree, warmer anomaly. We're comparing it to 1991 to 2020. If we were comparing this to 1951 to 1980, and we're talking about 1 degree, 1.5 degrees C. In other words, the zero would be down here. So when you look at these graphics, the first thing you should look for is the baseline. What is it being compared to? So when you compare it to the base of the last 3 decades, it's look at the last several years. Warm. Now, the last several years, within the 30 years, is still warmer than the average for those 30 years that it is part of. Absolutely mind-blowing. And it's warmer by a bit. It's basically what, 0.45 C warmer? That's considerable in such a short time. Now we're going to look at temperature anomalies by latitude band over the last 3 months, and we're going to look at the Arctic. So the plot shows zonal mean surface air temperature. Zonal, basically the latitudinal bands. Latitude is the x-axis, and so on. Again, NASA JIS, Goddard Institute. This is really a telling graphic. Wham. So what do we have here? Okay, these are the latitudes here. So minus latitude is southern hemisphere, positive latitude is northern hemisphere. Zero latitude, of course, is the equator. This vertical line right here at about minus 66 south latitude is the Antarctic Circle, and about 65, 66 degrees north latitude is the Arctic Circle. So temperature anomalies in degrees C, it goes from 0 up to 7. And what we're seeing here is that the entire planet, when you look at latitudinal widths, zonal widths, if you will, has warmed up, even over in Antarctica. Now you can say, what's going on here? It doesn't, like maybe 0.2, 0.25, 0.3 C warmer. What's going on here? Well, if you look at the latitude, this is about where the Antarctic circumpolar current is flowing. It's a current that is unimpeded, so it literally whips around, rings around the planet, and kind of got cold water there. And then look here at the Arctic. Now you see why I was saying the Arctic is warming 3 times faster. This is just amazing. We're talking from 75 latitude to the pole, we're talking in essence 6 degrees C warmer anomaly. This is incredible. Now, again, this is based on the 1951 to 1980, courtesy of Zach. Zach is the one that creates these graphics, and this is a very informative graphics. And so we have him to thank. But it's just astonishing what's going on. Absolutely astonishing. And again, this is looking at this 3-month period here. I mentioned before that when you compare, say, the state of Alaska, when you look at the historical average temperature month by month, the month that shows the greatest disparity, notice the greatest difference between the average and how much warmer it is, it's the month of October. And the reason for that is the lack of sea ice. Historically, in the past, sea ice starts forming late August, early September. By the time October rolls around, it's you got a pretty good sea ice out there. Well, the ice is not freezing up until mid to late September. There's still open waters in October, and any ice that is present is not very thick. So, in essence, there's a lot of latent heat energy being given off, and that's just keeping the air above the ocean and the landmass that much warmer. That's why October has been the warmest month for Alaska when compared to the average. So this shows it right here how much the Arctic has warmed. Now let's look at January 2021 specifically. Okay, so Antarctica was a little cooler. Okay, a little cooler, but again, the same situation. Much, much warmer. Over 8 degrees C by the time you get within 75 degrees north latitude. Absolutely astonishing. Same thing, 51 to 80 being compared to that baseline. Temperature knowledge by latitude band for every month of 2020. So previous ones, we showed January 2021 and then October through December 2020. Now we're going to look at every month. And no, okay, this is course data. So that's what the flat line ends at the pole. That's what this is. This is course data. This is another way of looking at the data. And so, for example, if you were to pick out, December is the white here. Okay, you can pick out March. Just look at the different colors here, and follow the graphic all along. And what's interesting is that it's the polar regions that show the most variations, and then some of the northern hemisphere temperate latitudes. But at the risk of sounding like a broken record, look at the Arctic. Right? And so the scale takes us from -2 to +9 C anomaly. And there's still warming at the equator, but much, much more in the polar regions, especially the Arctic. Same thing, 51 to 1980 baseline. And again, our friend Zach. And by the way, as you're watching my videos and you want to, you know, look at these graphics in more detail, pause the video, go full screen, pause the video, examine the graphics here. Now, I want to do this one here because this is looking at Siberia temperatures from July through December 2020. So here's the little wedge here. That's the region under consideration. We're looking at 2-meter air temperature. So it goes from -4 to +4. Now the baseline is here, and it's based on this data set, JRA 55, from 81 to 2010. And what we're looking at here is we're seeing the air temperature in Siberia. Looking at that. And if you look at the trend here starting about 1990 or so, even go back to the mid 80s, the trend is obviously increasing. You see the spike here. That reflects how very hot it was summer 2020. So something's going on there in the Siberian area. And by the way, here's the East Siberian Sea, and then you get to the Laptev Sea, the Kara Sea, the Barents Sea, and so forth. Now we can look at temperature anomalies by year, starting in 1979, going to 2020. Okay, now we're back to comparing to 51 through 80. This is the 2-meter level. Our friend Zach did a lot of work putting this together. And when you look at the overall trend, right, what do we see going on? Starting like '07, even going back to '05, and certain years like 2011, 2012, 2016. Here's 2020. Now, to orientate yourself here, this is Greenland. Greenland is right down here at about the 4 or 5 o'clock position. Here's Siberia. You can see that heat that was sitting over Siberia last year. So Alaska is right here, Greenland, right? So the orientation is exactly the same for all of these. Greenland, Alaska, Siberia, Scandinavia, Franz Josef Land, Novaya Zemlya. But you can clearly see how the planet has drastically been warming. And when you look at it, we're talking close to 5C above the global average compared to 51 to 80. That's how much warmer it was. This is extremely significant. Okay. Before we consider sea ice, a brief look at what's happening with Alpine glaciers. Okay, so in this graphic, we're showing regional cumulative mass change of reference glaciers. And you can see there's various ones, like the blue is Scandinavia, Western Canada, the USA. The red is Alaska. It looks like this line there. And, and so on. The Caucasus, Svalbard, Jan Mayen, Central Europe, etc. Then the dash black line is the average, the mean of the regions. Now, all these values are compared to 1976. And what you can see, and it makes sense that you would find the mean in between, in kind of in the middle of the various curves here. But what the trend is showing is a decrease in mass of the glaciers. Now, WGMS.ch is Global Glacier State. This is a website you can get more information on. A word about the scaling here and the units. Cumulative mass change, and this is in mass in water equivalents, sometimes also referred to as 1,000 kilograms per square meter. Basically, this is if I look at, say, 2020 right here, okay, and I'm looking at this orange, which is Western Canada and the USA, and I look across that looks like it's about minus 37, minus 38 times 1,000. So we got, let's take the middle, 37,500 kilograms per square meter less. So now if we look at the dash line here, that looks like about 23. That'd be about a loss of 23,000 kilograms per square meter. Then when you multiply by the size of the region, that gives you an idea of how much ice mass, snow mass has been lost. It is significant. So this is showing another way, but in like a histogram shape. So it's global annual mass change of reference glaciers. Again, the same thing. Annual meter units, meter water equivalent. Okay. Did I say mass? So meter water equivalent, which corresponds to tons per square meter, or 1,000 kilograms. 1,000 kilograms considered to be a metric ton. But overall, what do we see here? We're losing Alpine Glacier. So when you consider how many people rely on the meltwater for drinking, for irrigation, and we're losing that, there's going to be less meltwater each year. They're losing the meltwater. They're losing the drinking water. They're losing irrigation for crops. Water for that purpose. So this is very troubling. And we can see how you look at the last decade or so, there's been a lot of ice loss. This is yet another way of presenting it, kind of a single function here. And again, meter water equivalent, and it's just tanking. So you got to at the end of 2020, and that's about 24,000 kilograms per square meter overall. Very troubling. Okay, now let's look at the Bering Sea Ice. And we saw Bristol Bay had significant ice loss, and further north, the ice was pushed away from the shore due to winds out of the east. And then the wind blew from east to west, and it pushed the ice in a westerly direction. So this is the graph is courtesy of Rick Toman, who's associated with the Alaska Center for Climate Assessment and Policy. And what we see here, the blue line is 2020 through 2021, that the current winter, and this data takes you to about January 20 or so. The green line is the winter of 2019 and 2020. The black line is the median from 81 to 2010. So comparing to that 30-year median. Median is the 50th percentile, so we would expect to find half the years above it, half below it, and that is indeed the case here. Okay. So here's like Norton Sound, Kotzebue Bay, and so on. Here's the Bering Sea, the Bering Strait, into the Chukchi and the Beaufort. This is the region that was being examined. And as you can see, when we look at the median for 81 to 2010, 2019, 2020 was had a very slow, very late freeze up. It stayed below the median until about mid first third of February, when it got a little bit above, and then it really started melting quickly away. And by about mid March or so, it just dropped off. This data indicates that the current winter 2020-2021 is below the median. Autumn changes in the median decadal concentrations. So the left side would be the 81 to 90 decade, the right side 2011 to 2020. This is really cool. Well, very telling. Much of the Chukchi Sea has lower concentrations of sea ice in November currently than compared to October in the 80s. Whoa, let's take a look. This is then, this is now. So the top two panels, October. The bottom two panels, November. Note a word about the scale here. Think of this as, percent. Think of this as albedo, how much sun energy is reflected back to space. The white is, of course, ice, and this would be multi-year ice, thick ice. And then when you get to the dark blue, that's open water, which will be absorbing the sun energy, whereas the ice is reflecting the sun energy. So when we see the lighter blue and the even lighter blue, that's ice in various stages of freeze up. So you can still get sunlight penetration through this new ice. It can still happen. So here's October back in the 80s. And look at the sea ice. Here's the East Siberian Sea, by the way. We've got some pretty strong ice here. Excuse me. And we got ice forming right up to the shore off the East Siberian. Same thing off the north slope of Alaska. This, by the way, is where the Mackenzie River will be emptying into. But now look at October of this current decade, or the decade it just ended. This is open water. We don't see any thick ice. It's all ice that's forming. This is all open water. This is all absorbing sun energy. In fact, an interesting thing, when we look at Alaska, when we look at the historic average temperatures and then compare current average temperatures month by month and compare that to the historic, the month that's seen the greatest disparity between how much above average it is compared to the average is October. I mean, June, July, yeah, it's still warmer, but not by much, because June, July are the hot months up here. But October, you're supposed to get the ice forming, as indicated here. Well, now we have this open water, and it's giving off all this heat so that the air above the land stays warmer. And October, as it turns out, is the month for Alaska that has the greatest disparity. In other words, we see the highest warming on a month-by-month basis for October. It's kind of an interesting thing, and that does affecting what's going on here. Now let's look at November, back in the 80s. Lots of ice right up to the shore, thick, starting to, the ice is extending into the strait, into the Bering Strait, and so on. Right? Look at this here. Ice is not that thick. There's open water here, not on the way to freezing up. All that thick ice is gone. So when they say compare November now to October then, you can see why they're saying that. And they're saying there's less ice because there's less of the thicker ice. There's less of basically the multi-year ice. There's just less ice. Pretty incredible stuff here. And so when we see, just at the point, when we see something like this little shade here corresponding to there, that's probably like 2-year ice. This might be like 3-year-old ice. Where here we're getting like 4, 5, 6, maybe 7-year ice. It's all being lost. I'll have more to say about that in a moment. So you can see the drastic change in the ice. So now we're going to look at December. We're going to look at ice volume. So the previous graphic, we're looking at the extent. So that'd be square kilometers. Now we're going to be looking at cubic kilometers of ice. In other words, we're looking at ice thickness, which is a reflection of how old the ice is, how many years it is, what's the level of multi-year ice. So this is through biomass data set. And the AMET SLC, that's the American Meteorological Society. That's the website here. This is the data set site here. There's a couple of URLs for you to utilize. So what do we see here for the December Arctic sea ice? We see some, some cyclical stuff going on here, but you can see it's basically between 22 and 26,000 cubic kilometers. A little above here, a little below here, and then all of a sudden, boom, it just tanks. It tanks down to 12,000 cubic kilometers. That's a major loss, major reduction in volume, which reflects a major loss in multi-year ice. So here's the Arctic sea ice extent. Now we're back to the extent, so it's in square kilometers. This dash purple line, I guess it's purple, is the 2010s average. This, whatever color that is, what is that, burnt orange? Brick? I don't know. But that color there, that's 2021. And they show some others here, like I think that's 2016, that's 2015, that's 2018, just for comparison. But as you can see here, when we look at, and this is starting in January through, about February 23, 24 or so, we see that the ice extent is below the 2010s average. And this data is courtesy of JAXA, which is Japan Aerospace Exploration Agency. Back to our friend Zach providing us with these graphics. And we're looking at the white is the sea ice means for the 80s. I guess that's turquoise for the 90s, the blue for the 2000s, the purple for the 2010s, and this is the current year, 2020-21. And as you can see, it's pretty much tracking, maybe a little bit above, and it kind of dips below. Okay, but probably not significantly different. But here's the interesting thing. So the Arctic's current sea ice extent is currently the ninth lowest on record, but when you compare it to the 2010s mean, it is 55,000 square kilometers above. That's referring to what you see right here. Okay. Oops, wrong way, excuse me. But when you look at, compared to the 2000s, it's 550,000 square kilometers less. Okay, that's this. So you can see it's less, right, than that. It's going to be even more so when compared to the 1990s, and even more so compared to the 1980s. So we've got 890,000 square kilometers less than the 1990s mean, 1.4 million square kilometers less than the 1980s mean. And there's the URL for that information. So in other words, what we're seeing is a drastic loss of sea ice in the extent, how far it reaches out, as we just saw when we looked at the Chukchi Sea, for example, and the graphics that I just showed. You know, these guys here. So that's what's being measured, the extent, square kilometer coverage. It's just dropping. So we have that. That's what's going on there. Okay. More continuation, and we can see it kind of picked up again because we had some cool conditions happening, at least over Alaska. Okay, this is a graph that I really like. It tells a lot of what's happening. So what this is, it shows when the freeze of the sea ice begins, And then on the bottom side, when the melt begins. Now, this is the day of the year. So like January 1 would be day 1, February 1 would be day 32, and so forth. So when you look at the freeze onset, and this kind of goes back to about 1978 or so. When you look at this, now there's some cyclical aspects happening here, and that's probably due to some forcings of the Arctic Oscillation, maybe in conjunction with the Arctic Dipole and or the Pacific Decadal Oscillation. Be that as it may, what we see here is if we look at 1978, freeze-ups happen on day 259 of the year. Bring it all the way over to 2019 or so, and it's basically day 280. So in what, 40, 41 years, the time of when the ice begins to freeze is now occurring basically 21 days later. On the flip side, look at the, 1979, when it starts melting, that's day about 170. Again, we see some cyclical aspects, probably the Arctic Oscillation at work. And by the time you get to 2019, it's about day 160 that the melt begins. In other words, 10 days earlier. So we have the melt beginning 10 days earlier, the freeze up happening 20 days later. That gives us basically 30 more days of open water. And that's what this is showing, the blue area in between the two curves. This is showing the increasing length of open water. And there's an increasing number of days of open water. So now we have the open water. It absorbs all that heat. This is what's contributing to what Mars is going to say is going to be the blue ocean event. That is, according to some models, is going to happen within the next 1 to 2, 3 years, such that, and progress from there on out, such that by the mid 2030s, the Arctic Ocean will said to be ice-free year-round. So the first blue ocean event might be ice-free 2 months of the year, then 4 months, and 8 months, etc. And don't forget, open water just keeps absorbing heat, and will keep absorbing that heat so that the water is warm exponentially, which will then accelerate it such that we have year-round no ice. That's what's happening. There's another aspect to that, and that is what happens productivity-wise. When you have the ice, some sunlight energy can reach through there. I did a recent video on ice algae. When you have the ice there, you have algae that forms on the underside. Okay, algae do photosynthesizing. We got a little food system there, food web going on. Then as the season progresses, some of the sea ice starts to melt, so you get a little bit of stratification. Other primary producers kick in, get what's called ice edge productivity. Then later on, as more and more of the ice melts, then the oceanic diatoms, phytoplanktons, start doing their thing. Well, as we're losing the sea ice, I just showed you how the extent is decreasing, the volume is decreasing, and now we're showing you that the more days of open water. As we're losing the ocean, as losing the ice, you're going to lose the productivity from the algae and the ice edge. Well, then the oceanic phytoplanktons will pick up the slack, won't they? No, because the sun is still not quite high enough of an angle in the sky. The angle's still too low in order to activate for the phytoplankton, the oceanic ones, their electron transport chain, which gets the whole photosynthesizing thing underway. Those phytoplanktons need to have the sun at a higher elevation. That happens later on. So what happens now is you're not going to have productivity for those first couple of months of what's called the Arctic, productivity season. In other words, the net productivity for the Arctic Ocean will decrease. You're losing two sources of it, from the ice algae, from ice edge productivity. So yes, losing the sea ice and all the heating That's bad for the ocean, bad for the climate, bad for the planet. You can see uh, uh, why you have all the Arctic so warming up, right, 3 times faster than the rest of the planet. Well, now you're going to start affecting the food web and productivity in the Arctic Ocean. It's going to affect the organisms as well. So it's very important graphics there, and this to me is very telling. Let's look at CO2. So the average was 414 parts per million in December 2020. 10 years ago, 390. That's an increase of 24 parts per million in 10 years. Okay, and there's the URL for more info. So the red is reflecting seasonal variation. There's a seasonality to it. So you fit the black curve through it, and the trend is unmistakable. The ppms are increasing. In fact, I just saw recently that at Mauna Loa that the ppm levels was over 421 for CO2. And we know that you increase the CO2, temperatures increase. Follows it. That's established science. And we're seeing, as I showed you, we're seeing the temperatures increase. And as the CO2 continues to increase, there's a bit of a lag, but so will the temperatures. And when you actually take into account, how things are exponentiating, it's very troubling. The IPCC keeps insisting on using linear assumption, which is just scientifically wrong because the data is telling us it's exponentiating. And in fact, it now seems to be that the exponentiating is exponentiating in of itself. So it's basically becoming all these positive feedback loops kicking. It's becoming a runaway system. Some of the models I've seen suggest that temperature increase will be 7 to 9 C, maybe 11 C by 2100. Other models say earlier because of other aspects such as as the air warms, plants become stressed. They don't photosynthesize, they respire, which means they draw down O2 but increase CO2 because respiration, CO2 is a byproduct of it. So, and there are other factors going on as well. It's very troubling what's happening. Let's look at methane. Preliminary record high value in November 2020 of basically 1892 parts per billion. There is also a seasonal cycle. Whereas you compare it to November 2019, it was 1876 or so. So basically, it's increased by 15 parts per billion. There's your URL for the data set. And then people say, yes, methane is a much stronger greenhouse gas, but it doesn't last in the atmosphere. True. It oxidizes into carbon dioxide. So the warming effect is still going to persist. And as you can see here, there's a clear uptrend. That's why we're seeing more and more of looking at carbon dioxide equivalents. In other words, what is the methane levels, and for that matter, the nitrous oxide levels, how does that equate in terms of CO2 equivalent? And you combine those three, and the parts per million is about 560, 565, and it's drastically increasing. So when you consider something like the PETM, Paleocene Eocene thermal maximum, temperatures like 16 to 18 C above pre-industrial revolution levels, and the CO2 equivalent ppm level was well over 1,000. Something like I forget what the exact numbers were. It was like in the 1,200 range, plus or minus, maybe up, maybe a little higher, 1,300 or so. So if we're at 560, and models are saying we're going to be 7 to 9 C above, we're basically going to be halfway towards the PETM levels. It's just nuts. So there's a lot of it's all coming down really hard and really fast, and all at once. I mean, you look at everything that's going on with the with the conditions, the drought, the fires, the storms and so on, and the wild swings in weather extremes. Yeah, climate change is happening right now, folks. It isn't something that's going to be, down the line in a couple of decades. It's taking place right now. So there's the latest update. You probably have noticed I try to bring these to you on a basically regular basis, almost like a quarterly report, if you will. This is the final word. I want to tell you about the crazy conditions in Alaska for the month of April. Now, Alaska, for about February 1 or so, this is interior Alaska in the Fairbanks area where I'm at. It pretty much snowed every day. Sometimes it'd just be little flurries, whatever. Other times it'd be, several inches, 4 to 6, 8 inches or so. Come April 1st, wasn't a very funny April Fool's Day, that's for sure. We just got hammered with like two major storms after one and after the other. So that's it dropped almost like 30 inches, 2 to 3 feet, just major dump. Now, April for interior Alaska, not the coast. Interior Alaska is historically the driest month of the year. Very little precipitation, if any. In fact, the previous record snowfall in April for a 24-hour event was like 4 inches. We just obliterated that with like 18 inches for one event and 12 inches on another event. We just obliterated it. And then the snows finally stopped. Yay! Right? Nope. The temperatures then cratered, just dropped. It got so cold that some places were setting new record low temperatures, and other places getting very close to setting new record low temperatures. And we're talking minus 50. Yeah, 50 below Fahrenheit. Minus 50. It's like, holy shit. It was just absolutely insane. And keep in mind, this is April, where, Fairbanks, right now, we have over 15 hours of daylight, and we're getting these crazy cold temperatures. Meteorologists are now saying that this cold snap, with in the snowstorm that went with it, was of historic proportions. And it was funny looking at the maps of the Arctic. The whole Arctic is temperatures much warmer than average. 4 to 6 C warmer than historic average with the baselines that we've discussed. Then you look at Alaska, it's like 6 degrees C cooler. It's like a black hole of something here. But it was just absolutely crazy. I mean, now it's about 45 Fahrenheit, and things are melting. It seems to have gotten into a more typical pattern. But yeah, the first third of this month was just absolutely insane. Goes to show you, crazy stuff is coming down the pipe, folks. Anyway, thank you for your time, and we'll talk soon. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.